Hello and welcome back to Calculus2 section 10.3 on Infinite Series, where we are going to talk about the series in general, what it means to converge or diverge, and then finally talk about geometric and telescoping series. So we're going to start first with a definition that the series is the sum of the sequence. So last class we learned that sequence is a ordered list of numbers, and you know that the sequence AN had commas because it was a list. While series is the sum of that list, which means it will have pluses in between all terms. Notation is summation of AN, and that's simply going to be A0 plus A1 plus A2 plus A3 plus A4 plus, and I'll put 3 dots here. You have this symbol summation, sum. You have seen this before in chapter 5, and you are going to have hopefully greater understanding today. Before we go and do any of this stuff, we're first going to distinguish between what we call finite series, which is summation from, let's say, 1 to m of an. Well, n equals 1 to m. And infinite series, which is, let's say, n starts at 1 and goes to infinity of an. Now, we don't care about finite series at all because they're boring. They always converge. If you have 3 terms, if m is 3, if you have 100 terms or 100,000 terms, you can add all of those terms using either calculator or computer or whatever. And anytime you add a finite amount of numbers, they will always add to another number, so they're always convergent to a sum, and we just don't care about them. It is the infinite series that we care about, because infinite series can converge or diverge. And we only focus on infinite series, and if you look at the sheet I gave you, you will see that every single series in the second column has infinity on top. They all go to infinity because this is infinite series, right? And then they give you one column with conditions for convergence and another column for conditions of divergence. So, right, infinite series can converge or diverge. Finite ones always converge, so we don't worry about finite series. There is nothing to learn there. Now, what does it mean? What does it mean for series to converge? It's different than the sequence, right? Sequence converges if the limit is finite. Now, for series to converge, really? There we go. All right, so if the sequence of partial sums of a series converges, we say series converges. If the sequence of partial sums is just a lot in this sentence, but this sentence is, the meaning should have been read, but Now, let me give you an example of what I mean. If I say that I have a series of 3n, I don't know, plus 1, whatever, going from 1 or 0 to infinity. And I want to know if these converge or diverge, right? Converge or diverge. The long way, the annoying way to do this is to create the sequence of partial sums. So partial sum P0 is just when you plug in A0, so that's going to be 3A0 plus 1, and that's going to be, when you plug in 0 for n, that's going to be 1. Then P1 would be P0 plus P1. So we are going to use the old value, and then we're going to calculate one more, right? So we are going to have another one of these. So we have the old one plus, and now I'm going to have 3 times 1 plus 1. So this is the new term, which is the A1 term, right? And that is going to be 4, 5. Then P2 is P0 plus P1 plus P2. So that's 1 plus 5 plus, and now I have 3 times 2 plus 1. So that's going to be 6, 12, 13. And then I'll have P3, which is P0 plus P1 plus P2 plus P3, which is going to be 1 plus 5 plus 7 plus, and the next number is 3 times 3 plus 1, which is 10, and 13 is 23. So let's do a P4, but I'm going to abbreviate. That's P0 plus dot 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 plus P4. And that's going to be 1 plus 5 plus 7 plus 20. No. Wait.
It shouldn't be plus 7, I think.
No,
Plus 13.
No, plus 7 makes sense, because that still goes into A2, and A3 is going to be...
So
Yeah.
you said P2 equals 13.
No. Oh, you're saying, because plus 7 would be the 2 inside.
What the hell am I? Oh, these are not P's, these are A's. Holy nightmare. I am. Yeah, such is holy nightmare. A0, A1, A0, A1, A2, A0, A1, A2, A3, A0, A4. There we go. Holy nightmare. So we add all of the values from before, plus 10, plus, and now we have a next one over here, which is when I plug in what? 1 plus blah, blah, blah. It's over here, just be a 0. There we go. 1 plus 5, 7, 10, and then A4, that's 3 times what? 3 times 4 plus 1, that's a 13 right there. So 13, 20, 36, 36. Excellent. All right. And that's going to go forever.
I have a question.
Yeah.
After P2, it remained 1 plus 5. Why isn't it 1 plus 4 on P3? It's 1 plus 5 plus 7. Why didn't the 13 remain for A2 on P3?
Plug in 0. Hold on. Let's. I plugged in. I put P's instead of A's, so I messed up. So first number, n goes from 0, right? N goes from 0 to infinity. So since the n goes from 0 to infinity, the first value for n would be 0. We plug in 0 for the first number. 3 times 0 is 0, plus 1 is 1. Then the next partial sum is when I only add first two terms. I already know a0 is 1, so just carry that down. And then a1, I plug in 1. 3 times 1 plus 1. So altogether that's 5. Now, a0 is 1. A1 is 4. Four. And then this one, and then the 7, and then 10. Okay. 6, 10, 12. That's 10, 21, 22. And then 25, right?
35.
No. 35? 12, 25, 26, 10, 22, 23, 35, yes. So the sequence of partial sums, is this going to be the indicator of how day is going to go? We might as well quit now and just have the rest of the Saturday in peace. If I can't add numbers. All right, so 12, 22, 35, ... So I just made 3 mistakes in one, I think. So this thing over here is called sequence of partial sums. Guys, this is the long way of doing things, which is why we want to learn the tests, so we don't have to go through this annoyance and horror every time. So what we see is we have some kind of series. We look at the sequence, which is 3n plus 1. That's your an. And then you go n equals 0, n equals 1, n equals 2, n equals 3, n equals 4 to generate a0, a1. We did that last class. So now that you have this, these numbers, you can generate partial sums, right? Partial sum 0 is just a0. Partial sum 1 is a0 plus a1. You always keep adding one more term and one more term. And that gives you this sequence of numbers. Now, when you take a look at this sequence of numbers, you can call it Pn. The limit of Pn as n goes to infinity is going to be infinity. And that means that the series 3n plus 1 will diverge because it adds to infinity. And that's what this sentence here means. If the sequence of partial sums, this is the sequence of partial sums. So if the sequence of partial sums converges, then the series converges. Well, if you look over there, we know that for the convergence of the sequence, you have to have a finite, not a limit. We don't have a finite limit. So that means that the sequence of partial sums diverged, and because the sequence of partial sums diverged, the sum diverges. Here is another example. Hopefully this one goes better on addition for me. Summation, let's go again, 0 to infinity of 1 over 2 to the n. So looking at this problem, I have my an to be 1 over 2 to the n. So that's the sequence that was within the series. So an equals 1 over and 2 to the n, that's a sequence. And then if you put that in a sum, that means you're adding all the terms, then it becomes a series. And now we go P0 is just when you plug in 0, we get 1. P1 is, I almost wrote P again. A0 plus A1, which is 1 plus 1/2, which is 3/2. P2 is A0 plus A1 plus A2. That's going to be 3/2, right? Because that's this much. So that's 3/2. So copy 3/2 and add new term, which is a quarter, right? Because that's A2, n is 2, 2 squared is 4, so 1/4. And when you add all of these, you get 7/6. 7/6. 7/4, that's what I said, please, 7. Yeah, we're going home after this exam. A0 plus A1 plus A2 plus A3 is 7/4 plus 1/8. That's going to make this into 14 and 1, 15/8. P4 is A0 plus ... A4. And that's going to be 15/8, which covers everything up to 3, plus 1/16. So that's going to double everything, and that's going to make it to 31/16. One more, and then we're done. P5 is A0 plus ... plus A5. So 31/16 plus 1/32. So now 32 double 62, 63/32. So my Pn, which is the sequence of partial sum, this will go forever. Put the 3 dots like that. It will go forever. P6, P7, P8, P9, P1 million, P10 million, P100 billion, and so on. Right? So you can go as far as you want. Yes?
So why is P0 1? Like, do we just assume it being 1?
No. Where P0 is just the A0 term, and A0 would be 1/2 raised to the 0, which is 1 divided by 1, which is 1. Right? This A doesn't look too happy. All right. So now the first term is 1. The second term is 3/2. The next term is 7/4. The next term is 15/8. Then it's 31/16. Then it's 63/32. So what is my sequence here? How do you know that? Did you?
Because all the numbers are just barely off of 2 as they're increasing.
Aha. They are barely off of 2 as they are increasing. I like that. So can we make this Pn into a formula if I put over 1 over here? What would be the formula for it? Well, clearly there is some kind of a division. Then what? What's happening for denominators?
It's 2 to the n.
Excellent. Denominator is 2 to the n. And what's happening on tops? It's not odd numbers because you are missing a lot of odd numbers. You're missing 5, you're missing 9 and 11 and 13. So if you are missing odd numbers, you can't use that. But what else can we get out of these?
Like 2a plus 1.
Is it 2 to the n plus 1 minus 1?
2 to the n plus 1 minus 1. 2 to the n plus 1, like this.
That's one thing.
So what's 2 to the n? Let's see. 2 to the n, if n is 0, we have to start at 0 because you want to start the bottom at 0, right? 2 to the n over here, when it's a 0, you get 1. When it's 1, it gets you 2. When it's 2, it gets you 4. So we start at 0. So 0. So 2 gives you 1. 1 plus 1 is 2. Yeah, nice. You can see all my computer science geeks now flourish over here. All right, great. Well, it's finally your 5 minutes, right? So far it was all for mechanical and electrical. Now finally, well, this still for electrical engineering. I mean, you can't do signals without this stuff. So, yeah. Anyway, we have this. So now I have a formula that I can take the limit of. So I get to do limit n goes to infinity of 2 to the n plus 1 minus 1 over 2 to the n. And now it's in the hands of the limit. Can you do the limit for something like this? And this limit looks terrifying, but if you know limit properties from 2.3, then this limit is a joke. So last class I told you 2.3, 2.5, 4.7 from your Calc 1. If you don't know these sections, this part of Calc 2 is going to be living hell, right? So here are the properties. A property of the limit which says that if you have addition and subtraction of terms, you can separate in two limits. Well, you have a minus in the numerator, which means that this can split into two fractions with a common denominator of 2 to the n. So this immediately splits into two separate limits. One is 2 to the n plus 1 over 2 to the n, minus another limit, n goes to infinity, of 1 over 2 to the n. So this is basic property of limits. Now we use another algebra property, which says that 2 to the n plus 1 is 2 to the n times 2, right? You can split, we say peel off one of the 2's. So 2 times 2 to the n over 2 to the n, minus the limit, n goes to infinity of 1 over 2 to the n. These guys cancel. Limit of 2 is 2 minus 0. Because when you divide 1 by infinity, you get 0. So this goes to 0. And all we have is 2 minus 0, which is 2. And we move on with our life. So now, this sequence of partial sums converged. So we say, since Pn converged, summation of 1 over 2 to the n from 0 to infinity converges. And that's the end of the story, right? So if the sequence of partial sums converges, the series that generated that sequence converges as well. And this is the long, annoying way to do these problems, because you saw there's a lot of calculations, a lot of stuff. Can we do better? And the answer is yes. These 10 tests that I distributed are going to be faster and better way to deal with this, because this is way too many steps. The first, you extract the sequence. That's easy. Then you go through the annoyance of calculating at least 6 or 7 of these, because you have to develop the pattern that you are going to take the limit of later on. And just coming up with that pattern, it's not always going to be the walk in a park. Some of you said, oh yeah, it's just 2 and 2, right? And probably some of you in the classroom were going like, what the hell, how did they come up with that, right? So doing that step is not easy. And then you have to take the limit later on. So it's a lot of stuff that we have to do, right? which is why we develop faster routes of doing these problems. As I said, though all of those derivative rules you learned before, like derivative of a polynomial is nx to the n minus 1, or derivative of sine is cosine, or derivative of ln is 1 over x, right? You learn those shortcut methods so you don't have to crank the long way, which was using that limit h goes to 0 f of x plus h minus f of x divided by h. Same thing you did with Riemann sums. You memorized all of the antiderivatives and all of those calculations, so you don't have to use the Riemann sum, which was that limit n goes to infinity summation and all of that stuff inside. These are the shortcuts for series, so you don't have to do this. Okay? So let's go with the first one of all, and that one is going to be called geometric series. Now, as I said last class, do yourself a favor. Whatever I write in red, you memorize it. And what I'm going to write in red now is the second row of the sheet I gave you, which is geometric series test. If, no, not if, sorry, for, this eraser works for a second and then stops. So for summation, n goes from 0 to infinity, a r to the n. We have two cases. R is in between -1 and 1. We have convergence. R is outside of 1. We have divergence. That's it. This is what it says on your sheet.
The sheet says for convergence, just the absolute value of R is
Less than 1. Yes, you can write it that way as well.
all right.
So either way, it's easier to see if it's in between two negatives. It's easier to see if it's in between two negatives. I mean, in between two ones, -1 and +1. Great. So if you know this, now that's, I'm going to put that on a cloud. We'll add more to it, but for now. And now, what does my problem 0 to infinity 1, 2 to the n looks like? Well, I'm going to write this as 1/2 to the n. And now when you compare the two, how much is your r? How much is r? 1/2. And that's less than 1 and it converges. You just look at it. You look at the problem. There are no calculations. You either know it or you don't. Your r is the number that it's raised to the n. R to the n. So since your a is 1 in this case, right? A is 1 and r is 1/2. So the only thing that we need is for r to be between -1 and 1, and the problem converges immediately. Without any calculations. That's all. So r was 1/2, and because r is 1/2, that's less than 1, converges, done. What can you tell me about summation, let's say 0 to infinity of 4/3 to the n?
That's greater than 1, so it's not going to converge.
R equals 4/3, bigger than 1, diverge, move on. This is, right? It needs to take you less than 15 seconds to solve this kind of problem, right? That's all it is. Summation 0 to infinity. I'm going to put the problem that was on the NGIT Calculus 2 exam 11 years ago. That's when I was there. So 2 to the n plus 3 to the n divided by 5 to the n. Can you add 2 and 3 into 5? No, you can't. But what can you do? Separate into two sums, because you have a plus in the numerator. So you separate this into two sums, 2 to the n over 5 to the n, plus another sum, 3 to the n over 5 to the n.
Because both of those are under 1 with that.
Excellent.
How would it converge?
So,
Because you're treating them both separately.
yep. So we have one more algebra step. 0 to infinity, put this into 2/5, then put this one into 3/5, and r is 2/5, and r is 3/5.
So would this follow the same rule that if either of those didn't converge, the whole thing diverges?
If either of these, yes, remember what divergence means. One of these added to infinity, right? So it doesn't matter that the other one converged. Divergence is, right?
Yeah. Okay.
It's like having two sticks of dynamite, right? Like one of them exploded. Like, okay, yeah, but, you know, the other one didn't go off. Like, really?
Well, the only reason I'm saying that is just because this is kind of trivializing the last 5 hours we had with you. That everything we learned last week is just to show us that, oh, we could have just done 5 hours of work in 15 seconds.
No. Sequences are necessary for convergence because there will be some stuff that will be working with it. But now, this is specific for geometry. We'll have a lot of others, right? A lot of other cases that we will have to deal with. So, what we learned so far for geometric is just this one aspect of it. You look at R and you know whether it converges or diverges. That's it. That's all we know so far. Now, what's the next piece of information that we have to learn for these? If geometric series converge, we can compute the sum. Look at your comments box on a paper I gave you. It says that the sum is equal to a divided by 1 minus r. So we can figure out what they add to by computing this formula. Great. So now we have our summation of 1 over 2 to the n from 0 to infinity. And now what we have from here is we know it converges, right, because r is less than 1. So we know that a is 1 and r is 1/2. So sum is equal to 1 divided by 1 minus 1/2, which is 1 over 1/2, which is 2. So this series adds to 2. Series summation 1/2 to the n converges to 2, meaning adds to 2.
How did we know that A was 1?
Because there's nothing here.
Oh, okay.
the form is,
Yeah, I forgot that whole.
no, it's okay, summation AR to the n from 0 to infinity. So A is in front of whatever, A is the whatever is not to the n, right? Okay. One more. Summation of from 2 to infinity of 3 1/4 to the n. What can we notice on this problem?
You start at 2, non-infinity, that's not at 0.
Started at 2, not at 0. Good eyes. Does that matter?
No.
This one has 2 terms less, right? N equals 1 and n equals 0 are not in the sum. Those would be big numbers, right? The biggest, right? It matters a lot, actually. So this is the time to write in blood. In order to calculate the sum, we must make sure that the series starts at 0. And this one starts at 2. And that is an issue. Our formula doesn't work now until we fix this problem. So we have to fix this problem. And what we are going to find out as we are fixing this problem, that this 3 over here is a lie. Yeah. So let's go and do this. So how do we do this? We are going to do something that is called shifting the counter. Nice. Well, nice too. Shifting the counter. That's the procedure. Now, those of you going to differential equations eventually, pay the close attention and do not forget this, okay? Your chapter 3, all of the problems in chapter 3 will depend on this. So you have an entire chapter 3 hanging in balance over the procedure I'm going to do now. If you're not going to differential equations, you might see this on one of your tests, whether it's final or test 3. But the rest of you have the whole chapter coming up. All right, so what we have for the shifting the counter, we have to match the counter to start at 0. Counter starting at 0. So now what I'm going to do is I'm going to actually rewrite this, say n starts at 2. I don't like that, but we are here to fix it. I don't like that n starts at 2. So naturally, we'll subtract 2 on both sides. If your counter started at 7, you will subtract 7 on both sides. Your job is to shift it back to 0 by subtracting whatever is there. So now what you have is n minus 2 is equal to 0 below the series. And we don't like n minus 2, so we are just going to pull off the substitution and call this one k, or m, or whatever you want to call it. I call it something else. So this procedure here gave us the substitution that we are using, and substitution now is k equals n minus 2. So now, all of this tells us that the new series is k equals to 0. Because I subtracted 2, I got n minus 2 equals 0, and I'm renaming n minus 2 into k, so k is 0. And I have my 3, and I have my 1/4, but now I am changing all n's with k's. So what's my n equal to?
N minus 2.
K. K equals n plus 2.
I need to substitute n. What should I write instead of n?
K.
K plus 2. Great. K plus 2. So this is the substitution that we have to go through to make this equal to 0. Now it matches the formula for the series to start at 0. Awesome. But what did we just mess up?
You just added another constant.
No, see this now plus 2 over here? Yeah, right? But that's an easy fix, luckily, right? You can peel off 2/4 and then it will just be k.
Are you just substituting for the minus 2 where you have k plus 2 there?
Yeah, we have to, we are replacing n because we can't have n's anymore, right? We have to remove the 2, and as a collateral damage, right, of substituting and changing n equals 2 into k equals 0, we change them into k plus 2. So now we just need to peel off the 2/4, which is luckily easy thing to do. So you have 3 times, and now here's my 1/4 squared, and here's my 1/4 now to the k. Finally, the problem is transformed into k equals 0 to infinity, 3/16, and then 1/4 to the k. Remember how I told you that original a is a lie?
You move the extra bits into the A, and that's all.
Mm-hmm. So those extras are now in a, so your a is 3/16. Your r is 1/4, and you can finally calculate the sum as 3/16 minus 1 minus 1/4, and that becomes 3/16 over 3/4. 3's will cancel, and everything adds to 1/4. First off, the most insane thing is that infinitely many numbers would actually add into 1/4 at the end, right? That's what this convergence means. You're adding infinitely many numbers in this series, and they add to a finite value. In this case, is 1/4. So that's really awesome. You will do this procedure many times in chapter 3 in diffq to the point where you'd actually do all of this in a single step, going from one to another. You didn't believe me that when I told you about the derivatives, that you will be taking the derivatives just by looking at it, right? You will be integrating, by the way, you just look at it, right, and you're done. Remember how you said, oh, integral of dx of x plus 2 is just ln of absolute x plus 2. The first time you saw that integral, you had to go through u sub, right, and write 5 steps to get to the answer. And finally, when you did 5,000 problems in partial fractions, you just said, oh, ln x plus 2, absolute x plus 2. It was just like that. This shifting the counter will be like that when you get to differential equations, because every problem will have it. You will have to, because once you start taking derivatives of power series, it will be, every time you take one derivative, it shifts counter by 1, and then you have to bring it back so you can equal them all to solve the rest.
So does this mean that the equation of the function starting at 2 to infinity, the summation of all those area of the curve is equal to 1/4?
There is no curve here.
Isn't
These are just dots. you're adding just the y values of the dots. That's all. That's sum.
So
When you have the line, you talk about the area under the curve, because you talk about the area of the curve because you have the function times dx. So function times dx gives you the area, right? But over here, there's no times dx. So there's just y values that are being added. Right? The graph of a sequence. The graph of the sequence 1 over n is dot, 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 dot. There's nothing in between. So if I am adding these, this dot is at 1, this dot is at half, the next dot is at a quarter, right? Sorry, at a third, and then at a quarter, and so on. So it's 1 plus a half plus 1/3 plus 1/4, right? And you keep adding them forever.
How does this apply? What does each dot do when you add them all together? Is it like an average?
No, it's just basic sum. Like you have 5 apples and you add another 3 apples. Just have infinitely many halves and thirds and quarters of an apple, and will they actually compile an apple, or they will just add infinitely many apples?
It's not really different.
All of this stuff now is abstract. Chapter 11 will clear a lot of that up when we do power series and your chapter on differential equations, which I mentioned is using power series to solve differential equations. So most of this stuff over here, it's like a precursor of very little calculus in chapter 10. I mean, if you want to call limits calculus, then sure, every problem is calculus. But we're only going to see derivatives a few times. We're only going to see integral in one test, right? Integral test, so that's 1 out of 10, right? So we're going to see very little derivatives and even less integration in the entire chapter 10. It's mainly algebra, and you memorizing these tests. And if you don't know these tests, there's simply nothing you can do to solve these problems. So you need to know the entire sheet. And we just covered and finished geometric series. So for geometric series, it is very important to observe R, and if R is between the -1 and 1, series converges. If it's 1 or more, or -1 or less, then it diverges. So to solve, just if you're looking for convergence or divergence, you will just look at R, and within 15 seconds have your solution written and done, right? 10 seconds. If you need the sum, it's extremely important for these two to line up to be exactly n is equal to 0, and then n as the exponent. If anything is off, you have to do shifting. And the procedure to shift the counter, right, to use the summation formula, is outlined here as you subtract whatever is there, and then that gives you what the substitution is. Make sure you substitute the other one, and then fly through calculation to come up with the summation at the end. So that's called geometric series. And in case that you have a couple of geometric series linked together, like this NGIT exam problem that was on the test back in 2008, and I believe that they picked this problem because they were seeking if anyone is going to make a mistake and add these into 5. You can't add them to 5. So if any of those diverged, then the problem would be divergent. So you have to be careful. So if I have a problem that has multiple series, like summation of 7 to the n plus 3 to the n divided by 5 to the n from 0 to infinity. As soon as you split this up into 7 over 5 to the n plus, summation of 3 to the 5 to the n, this is the one that blows up, right? This is the one that converges, but together they have to blow up because this one added to infinity. This one maybe adds to 3, but 3 plus infinity is still infinity. Divergence simply means the terms you're adding add to infinity. There is nothing that the second series can do, right, to make everything convergent because this one already blew up, right? So we have to be careful, and it's pretty much the same. You had this idea earlier in your improper integrals where we had maybe multiple integrals at the end, and I said, you know, you had 4 integrals in one case, and I said just one of these. If one of these diverges, the whole thing goes to hell, right? Because it is that one that goes to infinity, and the others can't bring it back, right? Once it adds to infinity, it's done. That's geometric series. The next one is telescoping series. The book doesn't make a big deal out of telescoping series because it doesn't have a test. It has a procedure to do telescoping series. This procedure is a little bit annoying, but it's less annoying than adding all of those numbers. So it's still worth looking at it. Telescoping series has, on the sheet that I gave you, has the two sequences subtracted within the series. So they use B's, right? Yeah, B. So Bn minus Bn plus 1. It doesn't have to be Bn plus 1. It could be Bn plus 2, Bn plus 7, whatever. And it doesn't matter where it starts. So the only one, well, technically 2, which matter where they start, are geometric and P series. You don't want P series starting at 0 because it's 1 over n. That would be 1 over 0, right, if you start at 0. So if you look at the sheet that I gave you, row number 4 is P series. That's next section. You don't want P series starting at 0. So that's kind of 1 or more. Geometric have to start at 0 in order for our summation formula to work. The rest of these, it doesn't matter where they start. So I am not going to put anything underneath because it really doesn't matter for our, right? And now there is a procedure here. And the procedure is pretty much the same as the procedure you use for improper integrals. You make your infinite series Bn minus Bn plus 1 or whatever, you make it into a finite series, and then you set so let's say M, and you make it into a finite series. And then you send that to infinity. It doesn't make a lot of sense until we do the example. So let's go with the example of summation of 1 over n minus 1 over n plus 2 from 1 to infinity. Now, I should really get up and just collect all of your pens and pencils so you can't write and you have to stare at the screen, because this stuff is so easy, but it's also easy to get lost. You will catch up on your own in 10 seconds, okay? So look at the screen, forget about writing, so you can be done with this test instantly. What I'm going to do is I'm going to set up a whole bunch of these sums. Let's go set up 6. And in these parentheses, I am simply going to write, this is n equals 1, n equals 2, n equals 3, n equals 4. So I am literally going to write out these terms by plugging in and calculating the terms. So when n is 1, it's going to be 1 over 1 minus 1 over 3. 1 over 2 minus 1 over 4. 1 over 3 minus 1 over 5. All I'm doing is I'm replacing n with what they should be. See? That easy. You're computing terms, but because you have 2 of them, right, you put them in parentheses. So just do these. So now you can just catch up in 2 seconds, right? You know what to do. So compute first 6 terms. Later you will figure out that you can actually do less, but you need to know where to start, where to end. Set up another 6 of these later on when you are done. Now these will need more space because we'll be writing a little bit more in them, but now this is going to be the confusing part, especially for those who are non-computer science majors. So I need you really to pay attention here. Now we're going to do the tail end of telescoping. And this is where we are going to go backwards. We are going to start with n equals m. Remember that I'm replacing. Now the term before that is m minus 1. Then n is m minus 2, then n is m minus 3, n is m minus 4, and n is m minus 5. So now I'm using the same thing except I'm replacing n with m, or m minus 1, m minus 2, m minus 3, and I'm going now backwards. So from the front, you start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you go all the way to the last term. If the last term is m, then the one before that has to be m minus 1. The term before has to be m minus 2, right? Because that's how you go backwards. You're subtracting 1. So for computer science people to just translate I equals I minus 1. You know what, right? To assign. And the other way is I plus plus. Okay, fine. Glad we understand each other. So now we're going to go and put this as 1 over m minus 1 over m plus 2. Identical, right? Because I just swapped n for m, and that's my last finite term. Go ahead, place m minus 1, compute, and go through all of these all the way to the end. So 1 over m minus 1 minus 1 over m plus 1, because now I was subtracting 1, right? 1 over m minus 2 minus 1 over m. 1 over m minus 3 minus 1 over m minus 1. It's m minus 4 minus 1 over m minus 2. 1 over m minus 5 minus 1 over m minus 3. There are 12 terms that I wrote out, and there's the dot, dot, dot over here, so that takes care of all of the infinity of the terms in between. What I have done is I used the same trick that we used for improper integrals. In improper integrals, when you said 3 to infinity, you change that infinity with b, and you say limit goes to b. Now, in the last term, or whatever it stays with m's, you will say send m to infinity and see if that, works out. So now what I'm going to do is, I'm just going to cancel. Do you see how many terms cancel? Do I have negative 1/3 and positive 1/3? Negative 1/3 and positive 1/3. Gone. Blue pair. Negative quarter and a positive quarter. Gone. Purple terms. Negative 1/6 and a positive 1/6. Gone. Thank you. Negative 1/5 and negative 1/5. Gone. Do you see how we have this parenthesis and this parenthesis here? They have both terms canceled. That means, since I have those two, that means that this term will cancel with a negative 1/7 in the next one. Because look at this. 1/1, 1/2, 1/3, 1/4, 1/5, 1/6. Wouldn't that 1/7 put the next one and I didn't write it? Well, I can't write them all. So 1/7 term would cancel in those there, and I'm going to use a different color. Let's go with this neurotic blue. That would cancel in there. Do we see that we canceled all of the terms? What are the only two terms that are left? 1.5. Now do the same cancellations backwards on the tail end. Do I have 1/m canceling? Yep. 1/m plus 2, I don't have it. I have m minus 1 canceling. M minus 2, yes. Here is m minus 2, good. I have m minus 3 canceling as well. As soon as you hit, going forwards, as soon as you hit the parenthesis that cancels both, guaranteed to cancel everything afterwards. Going backwards, as soon as you hit parenthesis canceling both, it's guaranteed to cancel everything else. So I'm going to use now green to cancel this over here, and one more of these colors. Let's go with yellow. There we go. So these terms would cancel in there eventually if you wrote more terms. And what's left? What's left is 1 plus 1/2 plus the limit of m goes to infinity of negative 1/m plus 1 minus 1/m plus 2. Would you agree that these go to 0 as m goes to infinity? Right? 1 divided by infinity is 0. So the whole thing is just equal to 3/2. It converges to 3/2.
Does it matter whether you write it improper or 1.5?
No. Whatever makes you happy, because this is a math class. Your happiness is our primary concern. Just like United Airlines, right? Just don't cross the line. That's telescoping. There are no hidden rules, no hidden agendas, just more annoying problems, okay?
Brute force.
Brute force, yes. This is the brute force, and it's still easier than actually doing all of the other stuff that we did. Because over here, you're just going straight for, you're plugging in numbers right away rather than, playing with a sequence, then figuring out the sequence formula, then doing the limit, right? This is faster. Now, the question is, can we make this more interesting? And the answer is always, of course, we can make this always more interesting. Everything in math you can make more interesting. Summation 0 to infinity of 1 over n plus 6 times n plus 7. Yeah, you're just going to get n squared and stuff, so it still doesn't work if you FOIL it.
That's because it's starting at 0 and not 1?
No, doesn't matter. You can start at any number. You can start at 10 if you want.
Is this something that we have to do partial fractions to account for?
There you go. It's the partial fraction decomposition that it's going to turn it into a subtraction of the two. All right. Partial fraction decomposition are on your exam next week, so you might as well do a quick review, refresher, right? On partial fraction decomposition. Guys, you have two linears, so let's go. A over n plus 6, b over n plus 7. Go, go, go. I'll be right back. n plus 7a bn plus 6b is equal to 1. A plus b equals 0, and 7a plus 6b equals to 1. From the first equation, b equals negative a, so 7a minus 6b equals 1, a equals 1, therefore b equals negative 1. Cool. So the summation was a over n plus 6 minus b, plus b over n plus 7. And when we plug this in, it becomes 1 over n plus 6 minus b over n plus 7. And that's it. So now we can do partial fractions because we have not b, 1. There we go. See, these problems are awesome, right? For killing time, carpal tunnel, lots of other different applications. You do partial fractions plus telescoping. I mean, come on, you can't beat that. No, actually, I'm kidding. You can. It's called the integral test. It's going to take 2 pages. This is quick. Now, guys, these numbers, 6 and 7, are by 1 apart. That means that only the first and the last parenthesis will give the contribution. You don't know this yet because you're just learning, but you see from n to n plus 2, they are 2 apart. That can be molded into a pattern, and the pattern simply says that whatever the difference between the term is, that's how many of these first ones survive. So if there was n and n plus 3, this one would survive as well. It's a pattern. So there is a much faster way of dealing with these problems rather than writing everything out. You just write the first 2 parentheses and the last 2 parentheses here, because you know that the first term the first term will survive, and then the last term will survive. So this is going to be, we're starting at 0, so 1 over 6 plus 1 over 7. 1 over 7 will actually cancel in here. And then when you go to the tail end, you would have 1 over m plus 7 and 1 over m plus 6, where m plus 6 would cancel in here. And just because they're one apart, you just know that the first and the last term are the only ones to survive. That's a pattern.
And the first parentheses isn't supposed to be 1/6 minus 1/6.
Oh, minus, yes. Minus over here. You're right. So this is 1/6 plus the limit of m goes to infinity for -1 over m plus 7. So it all adds to 1/6, converges to 1 over 6. One more telescoping problem, and then we're going to close the book on 10.3. We have a lot of examples that we can use. Summation, start at 1, go to infinity. Let's go with ln n minus ln n minus 1. I mean, n plus 1. ln plus 1. Oh, he's in Nepal now, so he's coming back in 2 weeks. So these are 1 apart, and because they're 1 apart, we can just set up first and the last parenthesis again. It is ln1 start at 2, sorry. Start at 2. So it's ln2 minus ln3, and over here is ln m minus ln m plus 1. So this one will cancel in here, this one will cancel in there, and we are left with ln2 plus the limit of negative ln m plus 1 as m going to infinity. So this becomes ln2 plus, very good, diverges. The limit of x is infinity, so the limit of x plus 1 will also be infinity. It's an increasing function. So the pattern that we developed earlier is, what to remember is that the distance between the two terms is how many of these parentheses survive. And for the top is the first terms in the parenthesis, for the bottom it's the last terms in the parenthesis. And the difference between the terms, right, in this case n and n plus 2, tells you how many of those in between. So if you want to work out the whole thing, sure. If you are remembering the process of canceling, sure. Usually when you have the shortcuts and patterns and so on, it's a double-edged sword, because if you don't remember some aspect of it correctly, you might end up using it in the wrong spot, using it the wrong way, or you can't remember because you memorized way too many of those. There are multiple ways, to mess that one up. So maybe learning the full procedure is beneficial. Generally, ln's and square roots, right? If they are just on n, they diverge. Those other ones converge. So that's it. That's 10.3. We'll take a short break. When we come back, 10.4.
Are we doing